here's a quick recap of what we did today in class about inverse functions, and you will notice that I am about to lose my voice, so I apologize for the quality of my voice in this video. In an inverse function, we are looking to see if a function undoes itself. In other words, or we find the function that undoes another function. So if I have f of x equals x plus 3, and for example I could put 2 in the function and I would get 5 out, I'm looking for the function that allows me to put 5 in the function and get back to 2. So if you thought about it a minute, you'd probably guess, oh, f of x equals x minus 3 is probably the inverse, and you would be correct. 3 and negative 3 are inverses of each other. They're additive inverses. So we put 5 in, we get 5 minus 3, and we get back to 2. If I have g of x equals 2x, we can put 3 into the function and we get 6. So what function would allow us to put 6 in and get back to 3 and would work for every value of x? Well, you would probably guess the multiplicative inverse. Instead of multiplying, we divide by 2, or multiply by 1/2. And so we have g inverse of x, and let me point out function notation at this point. There's g of x. The inverse notation means I use this little -1 to denote the inverse of this particular function. I put 6 in, I get 3. Now, I have h of x equals 2x plus 3, and I put 2 into the function, and I get 2 times 2 plus 3 is 7. And I'm looking for the function that allows me to put 7 in the function and gets back to 2. So if you'd like to, you might want to pause the video for just a moment and write down what you think the inverse function is. Many of you probably put x over 2 minus 3 as your inverse function. But if you put 7 into that, it doesn't get you back to 2. It's not correct. Why is it not correct? Well, we need to think about the order in which the operations are done as well. If you look at the original function, the first thing I did was multiply by 2, multiply x by 2, and then add 3. So in the inverse function, to undo that, we have to go in reverse order as well as reverse operations. So we have to subtract 3 first and then divide by 2. So the inverse function would look like this: x minus 3, the quantity, divided by 2. If I put 7 into the function, I should have written this with a 7 here. Inverse, h inverse of 7 is 7 minus 3 over 2, gives me back to 2. The big idea here is that we have to use opposite operations in the opposite order in order to get an inverse function. So let's take a look at this function right here. Here's the function, c of x equals 2 times the square root of x plus 3. If I put in 1, I'm picking deliberately nice numbers that will give me a perfect square. If I put in 1, I get 4. If I put in 6, I get 6. So what would allow me to go the other direction? How would I undo this? So think about this for a minute. Once again, see if you can figure out how you would write the opposite operations in the opposite order to get back to the inverse function. Okay, don't know if you've had a chance to think about it, but let's think about these operations. First of all, I added 3 to x. Then I took the square root of that quantity, then multiplied by 2. So in the inverse function, the very first thing I would have to do to x is divide by 2, then square it, then subtract 3. So it looks like this. Inverse, a c inverse of x is x over 2 squared minus 3. If I plug in 4 into the function, I get 1. If I plug in 6, I get 6. So I've checked. Once again, we're talking about the opposite operations in the opposite order. Now let's look at some other characteristics of inverse functions. On this graph, I have graphed the square 2 times the square root of x plus 3, and I did that by plotting some points. I put in -3, which would be the smallest value for x I could put in, and put in some other values that would make this be a perfect square, -2, 1, and 6, and I found the y values, and that gave me this graph right here. In order to do the inverse, I could plug in points. However, an easy way to always find the inverse function, and especially if you don't even know the equation of the inverse function, is to take all the coordinates that you just plotted for the original functions and swap the x's and y's. Because remember, the functions undo each other. So if the original function gives me 0 for when I put in -3, the inverse function should give me -3 when I put in 0. So if I switch those and plot them, I see that I get these points, 0, -3, 2, -2, 4, 1, and 6, 6, and this is the graph. Notice that it is just half of a parabola. Because the square root function only is one side of the curve, notice that I can't draw the entire parabola. I only want to draw this half of it to be the inverse of the square root graph, because this is just the positive square root. So I put a little domain limit here and say this is x greater than or equal to 0. So, a couple things you notice here. Big ideas. Plot points for inverse by switching x and y coordinates of the original function. That's one thing. And the other is notice that inverse graphs have this special symmetry. They are reflections across the line y equals x, and that's always true for inverse functions. Now, what's another way that, besides just thinking of opposite operations in opposite order, that we could find the inverse function? Well, since we are just swapping x and y all the time when we're doing inverse functions, I can take the original equation and replace the c of x with y, because that is another name for the y coordinate, and switch the x and y in the equation. So the inverse equation would actually have this relationship. Now solve that for y and I'll get the inverse equation. So solving that for y. Now I want you to notice the steps we took. First we divide by 2, then we square both sides, then we subtract 3. Exactly the same things we did when we thought about doing the opposite operations in the opposite order. Finally, at the end, rather than using y, I'll substitute my inverse function notation, c to the -1 of x, or c inverse of x is equal to x plus 2 squared minus 3. One last one I want to look at in this intro is f of x equal 2 to the x, which is an exponential function. And I made a graph, or a table of values for x, putting in 0. And I want you to notice that when you put in an exponent of 0 in an exponential function, that gives you the y-intercept. So my y-intercept here is 0, 1. Then I put in other values, 1, 2, 2, 4, 3, 8. -1 would give me 1/2. -2 for x would give me 1/4. I plotted all those points, drawing the line very neatly along here. I pointed out in class, I don't like it when you have an asymptote and you sort of make this go up like that, because it's not supposed to go away from the asymptote. It's supposed to just hug the asymptote like that. So it's just right along there. Now, like we did before, you can switch the coordinates and plot the inverse graph. And when you plot the inverse graph, you find out that, oh, that's a log function. Hopefully you recognize it, and you might guess that the inverse of 2 to the x is log base 2 of x. How do I do that using my method of swapping the variables? Well, if my original equation is y equals 2 to the x, my inverse is x equals 2 to the y. And the only way to solve for y is to use logs. So I can write that as log base 2 of x equals y. And you can write 2 to the y equals x. You can go back the other way. So my inverse function is, I think I used f of x here, is f inverse of x is equal to log base 2 of x. We'll go into more on inverse functions in the next video.